Thank you for coming to my presentation. My name is Mitsu Echeverria. I'm a PhD student at the University of Iowa. This is a work with my group at Iowa and a collaborator from Penn State. And today I will be talking about Phoenix, a device-centric cellular network protocol monitoring using runtime verification. So nowadays, we all have cellular devices, and we've all encountered the issue where we're suddenly lose connection, suddenly lose service. And we attribute it normally to, service disruption, right? Maybe the base station went down. But it actually, this could have been done because of an attack. And unfortunately, there's no way to distinguish this, and that's why our goal of our project is to give the user's devices the ability to detect undesired behavior. So what are some possible applications for this? Well, first of all, we could have a warning system, an application that runs and alerts the user, for instance, when they're eavesdropping on their calls. The next thing we can do is we can take this even further by deploying this inside a modem and let the modem take corrective action, which is a full-fledged defense. And last but not least, we could empower some honeypot devices to uncover, what type of undesired behaviors are occurring and, how often. But our main focus of our work is on the first two. And specifically, due to time constraints, we're going to be talking about mainly the warning system. For more details on the defense, please consult the paper. So now you might be wondering, why would anyone want to attack cellular networks? And the answer is actually because they power up many different applications, including safety critical ones. So for instance, you might recall not long ago about the the whole Hawaii and missile issue where an operator accidentally sent a message. But sure, this was a network operator error, but this could be very well carried out by an attacker. So in order to achieve this application-based warning system, what do we need? Well, we need for every message that's sent and received by the modem to be somehow intercepted and sent over to a monitor component, where this monitor component uses a attack signature database, essentially a repository of what different attacks look like. The monitor uses the previously seen messages and the new message to make a decision. For instance, if a non-desired behavior occurs, it needs to raise an alert. And this attack signature database obviously is pre-populated, so we need to come up with the signatures. And to do this, a security expert could do this manually, or they could use our optional component, which is called a signature synthesizer, to achieve this. So in order to carry out this goal, we need to overcome certain challenges. So for instance, the first thing we need to do is we need to be effective, right? Because if we overload the user with false warnings, they're going to disable it. Second, we need to be efficient. As we're adding any overhead, we don't want to drain the battery of the device. And last but not least, we want to be, sure, we can develop a tool that works great in the test bed, but we also need to make sure that it works just as well when we deploy it in the real world with real networks and real SIM cards. So as you might be imagining, this is a humongous problem, so we need to somehow reduce it to change the scope. So first of all, we're only going to be focusing on 4G LTE, other than other generations. However, we argue that we can simply switch one or two components and be good to go. The next thing, we are only focusing on control plane protocol attacks, and this is because this is a stepping stone for other destructive attacks. And specifically, we're only looking at attacks on the NAS layer, the non-access stratum, and the radio resource control RRC layers. And we're also only interested in undesired behaviors that are observable by the cellular device. So for instance, something could go on the network, but we're only focusing on things that the the cellular device can actually see from its vantage point. So before we talk about the main, our paper, let's talk about the contributions. So first of all, we are the first to design an in-device for the cellular networks a behavior detection system. And this system is called Phoenix. We then deploy Phoenix as an Android app and uncover undesired behaviors in 3 major US network providers. We deploy also Phoenix as a full-fledged defense mechanism. And we also show how we can automatically synthesize the behavioral signatures. So now we're going to talk about kind of the overview of the rest of the paper. So we're going to talk about our intuition and attack signature in signature representations. Then we'll talk about evaluation, and we'll conclude with a small demo. So now let's talk about the intuition in the signatures. So if we recall, this was our overarching goal, right, for the Android application. But to get to this point, we need to, meet some certain criteria. So first of all, we have to develop an effective signature synthesizer. We have to develop an efficient and reliable message extraction tool. And we need to develop an efficient monitoring system. So now we're going to be mainly focusing on the monitoring system, and then a high level talk about our signature synthesizer. So what's the intuition behind our work? Well, for GLT nowadays, unfortunately, it's plagued with different vulnerabilities, each affecting, each achieving different things. But if we look at these four, that I showed in the previous slide, is that they're actually all, violations of temporal ordering of events. So can we use this knowledge to take this even further? Okay, well, sure, we can develop signatures. But now you may be wondering, what are these signatures that I keep talking about? Well, for instance, let's imagine we have a universe of all protocol executions represented with this big blue circle, right? And there's a smaller red circle where, for instance, let's call that an attack alpha, where the attack alpha occurred in the red circle, in this case, T4 and T5. So if we call this red circle L, we can think of it as the rest of the blue circle as L star. And this is actually the signature that we want to use in Phoenix by helping it identify, the kind of separate the blue and the red, right? Whenever we move into the red, now we need to raise a warning as, attack alpha or undesired behavior alpha has occurred. So what different types of signature representations can we use? Well, first of all, we can use a deterministic finite automata, a DFA, where each DFA tells us whether or not, an attack has occurred or not. Similar to this, we can use a Milling machine where now also the output helps us identify if an attack has occurred and which one specifically. And we can also use something called passive linear temporal logic, which is a type of technology that is very well suited for this type of temporal ordering, property violations and analysis. So for the deterministic finite automata in the Milling machine, the implementation is quite trivial. It's just, just some nested dictionaries. You can think about it that way. And as for the passive linear temporal logic, we use a well-known dynamic programming algorithm. So now that we, kind of discuss these different monitoring or signature representations, let's talk about, their advantages and disadvantages. So first of all, DFA is highly efficient, and we can use an off-the-shelf synthesizer. So that's great. But unfortunately, it produced a lower F1 score than the rest. Well, for Milling machine, again, it's highly efficient. There's an off-the-shelf synthesizer, and in fact, DFA and Milling machine use the same, which is called RPNI, and it produced a slightly higher F1 score than DFA. However, adding an attack requires retraining. So if we recall, Milling machine had, n attacks per signature, right? But what happens if we find a new undesired behavior that we want to include in this, right? Now we have an n+1. We need to retrain everything and deploy the signature over to the device. On the other hand, PLTL actually is our best approach. It produced the highest F1 score. Additionally, the signatures that it produces are, human interpretable. But the main issue is that we don't have an off-the-shelf synthesizer. So this is something else that we have to overcome. And to do this, we develop our PLT synthesizer. So we get the idea. It's like, hey, we can actually reduce the formula synthesis problem into a SAT problem, right? So imagine we have a SAT solver. If we can somehow tell it, okay, these are valid abstract syntax trees of what a formula would look like, we could also tell it, these are the, correct labels that you can use for the formula. Then we can use our, then we can feed it our benign and attack traces and get whether or not this formula, is actually a valid in, and help in identifying the attack or the undesired behavior. So now let's talk about the evaluation. So you might recognize this slide as it's the same one as I use in the challenges, right? And that's because it is important to compare our, to really understand how well we overcame these challenges that we imposed, since the very beginning of this presentation. So let's talk about effectiveness, right? So now, in this line graph, we show the F1 score for different monitor signature representations, and different synthesizers. So as we can see, PLTL achieved a perfect F1 score with minimum traces, which is great. The bottom is the the size of the data set. So this is great. And then, but this is kind of a more simple problem. Now let's look at AK bypass attack, which is a little bit more complex problem. And we can see that, again, PLTL achieved a perfect F1 score with minimum dataset size. And this is great. As you can see, also DFA started to struggle, but not so much. But the main takeaway from this slide is that PLTL actually produced a high-quality signature with minimum dataset size. And this is important, as there's really no open source repository that we can go to and get lots of a high dataset size of some specific attack. So it's important to be able to produce a high quality signature with minimum dataset size. Now let's talk about efficiency, and we're specifically talking about power consumption. For instance, for message throughput and other efficiency tests, please consult the paper. But to measure the power consumption, we plug the Nexus 6 device into a Munson meter. These are the numbers that we got. So overall, we saw that on average, it maintained about the same. And really, all the monitors produced negligible overhead, which is great, right? And this is the main takeaway from this slide. That doesn't really matter what, which monitor you use, they all consume approximately about the same electricity. So this is great. So next, we need to see, how well our tool actually, behaves with real networks, real devices, and real SIM cards. So for this, we deployed the Android application on 2 Pixel 3 devices in 2 different geographical regions. So what we saw is that DFA produced some warnings, 6, 7, 4, and 4 respectively. Melee Machine produced no warnings, and PLTL, produced no warnings for one of them, and then 1 warning for each of the other operators. So at this point, we were kind of expecting, for instance, for all of them to be false warnings, but that wasn't the case. In fact, PLTL identified real undesired behaviors in 3 network operators. So what was going on is that the EM information message being broadcasted by the network that helps, provides, for instance, a time zone and maybe even time, was in plain text. And this can be somewhat of a dangerous practice, as this allows anyone really, in the middle to modify it and, for instance, change the time at the cellular device. And this puts, this can affect some like time-sensitive applications. For instance, you can think of it as, certificate validity check. And now let's talk about the demo. So here I'm gonna show a small demo on a Phoenix in action. In this scenario, we're going to be detecting the NUM attack, an attack discovered by Hussein et al. In an LT inspector. So on the left-hand side, we have the network and the base station. They are running on SRS LTE and an open source protocol stack for 4G LTE, and they have a modified to perform the NUM attack, right? And on the right-hand side, we have the Pixel 3 device mirroring its screen, running the Phoenix application. So here we're going to disable airplane mode and let it connect to the network. It's going to connect to the network, or at least attempt to. The malicious network, the modified SRS LTE, detects this attack and produces carries out the attack, and Phoenix alerts the user of what went wrong. But thank you for your time, and I'll be glad to take any questions at this point. Additionally, we would like to thank DARPA for funding our work.